Okay, in the last part of this talk we discussed general Smith maps, which include the J-holomorphic maps and associative Smith maps as special cases. We also state Smith's theorem, as well as our main results on the analytic aspects of associative Smith maps. To get started, we need yet more notation and concepts. So let M be a Riemannian manifold of dimension n, and let k be an integer between 1 and n minus 1. A k-fold vector cross product on M is a bundle map P, which inputs k vectors and outputs a vector, and is completely alternating in its arguments, and it satisfies two conditions. First, v1 cross up to vk is orthogonal to v1 and v2 and all the way up to vk. Moreover, the length of the output v1 cross up to vk is equal to the magnitude of v1 wedge up to vk. Okay, so a classic example of a twofold vector cross product, for example, is the ordinary twofold vector cross product on, say, R3. Let's let Vp of k denote the k-fold vector cross products on an n manifold. We'll need this notation later. Now, in view of the metric that we have on the Riemannian manifold, we can lower an index, and as we've been doing, we can recast the k-fold vector cross product P as a k plus 1 form. Let's call it alpha, and you can see the formula for alpha right there. It's the ordinary one. And you can check that alpha really is a k plus 1 form. It is genuinely alternating in all k plus 1 of its inputs. Moreover, one can check that alpha has comass 1. Okay, this follows from, well, what else do we have but the definition of a vector cross product? So, of course, if alpha is closed, and this happens in many cases of interest, then alpha is, in that case, a calibration. Okay, now just a word on notation. What we have is a Riemannian manifold and a choice of vector cross product P. So really what we should do is denote that as M, the inner product, and P. However, in order to align the notation with what's done in symplectic geometry, I'm going to commit a slight abuse of notation and denote the data by M, alpha, and P. That's maybe not the most accurate, but it's convenient for the sake of analogy. So we've already seen some examples of vector cross products. For example, on any oriented Riemannian n manifold, the Hodge star operator on n minus 1 vectors, that is an n minus 1 fold vector cross product. So when n is 3, you get the familiar two-fold vector cross product on an oriented Riemannian 3 manifold. Also interesting, believe it or not, is the case of one-fold vector cross products. So let's say you have an almost Hermitian manifold, necessarily of even dimension. Okay, this entails having a Riemannian metric, a non-degenerate two-form omega, and a compatible almost complex structure. It is almost Hermitian because we're not requiring omega to be closed per se, nor are we requiring J to be integrable. In this setting, the almost complex structure map J is a one-fold vector cross product. And it turns out, somewhat surprisingly, that these two examples are half of all the possible examples, really. There is a classification theorem, a rather classical one, actually, due to Brown and Gray in '67, saying that there are only 4 types of vector cross products up to isomorphism. So, up to isomorphism, every k-fold vector cross product P on a Riemannian manifold of dimension n is one of the following 4 types. Type 1 is as above, where you have an n minus 1 fold vector cross product given by the Hodge star, and the corresponding form alpha is just the volume form. Okay, this is equivalent to specifying on M in orientation. Also above is type 2, for lack of a better term, that occurs only in even dimensions. You can have a one-fold vector cross product given by an almost complex structure. Of course, the corresponding form alpha is the 2 form given by, well, the almost symplectic form. This data of the choice of P is equivalent to specifying an almost Hermitian structure. Finally, there are these 2 exceptional types that can occur only in dimensions 7 and 8. We've already seen the 7-dimensional one. It occurs when you choose a G2 structure. It's really equivalent to choosing a G2 structure, phi, and as we've seen, phi induces a 2-fold vector cross product that I'm going to continue denoting Q. There is an 8-dimensional cousin to this, that occurs whenever you have an 8-manifold with a spin 7 structure. In that case, you get a 3-fold vector cross product. I'll just call that Q3, and the corresponding form alpha is a 4-form capital Phi. Okay, and it's essentially the same thing as the G2 case, just everything, I guess you just add 1 to everything, more or less. So every vector cross product is one of these 4 up to isomorphism. Okay, so with this in mind, we can finally define what we mean by a general Smith map. So as a domain, we'll take sigma p. Okay, so that's just any oriented conformal p-dimensional manifold where p is at least 2. All we have is an orientation and a conformal structure, but I'm going to denote the orientation, or just remind ourselves of the orientation, by the volume form. That's a p form, of course. And the conformal structure by the Hodge star, which, as we now know, is a p-1-fold vector cross product. For the target of the Smith maps, we'll take an n-dimensional oriented Riemannian manifold with a p-1-fold vector cross product capital P. And again, the induced form is a p form. So what we have is a p form on both the domain and on the target, and we also have p-1-fold vector cross products on the domain and the target, despite the fact that the target has dimension n. So a map U from sigma to M is said to be a Smith map if it satisfies the first order PDE that you see there. Okay, so what this says, just like in the associative Smith case, this is clearly a generalization, is that Smith maps intertwine the p-1-fold vector cross products given by the Hodge star on the domain and p on the target. They intertwine them up to this somewhat strange conformal factor. Notice that this conformal factor goes away when p equals 2, for example. It also goes away, for instance, when p is 3 or 4 under the condition that U is an isometric immersion. Okay, and by goes away I mean equals 1. So I guess the one-sentence tagline would be that Smith maps are conformally cross-product preserving. And now, in view of the fact that vector cross-products are, in some sense, can be recast as forms, there is an equivalent characterization of Smith maps in terms of forms. Okay, so a map U is Smith if and only if it is weakly conformal and satisfies this equation. It pulls back alpha to be this particular multiple of the volume form on sigma. Okay. So what data have we really specified when you have a Smith map? Well, what data do you need? So again, on the domain, you just need an orientation and a conformal structure, but on the target, you need this p-1-fold vector cross product called capital P. But by the Brown-Gray classification, there are only 4 options for P. And so consequently, there are only 4 types of Smith maps, depending on what P is. If you take capital P to be a type 1 vector cross product, meaning the Hodge star, then your Smith maps are not very interesting, they're just conformal diffeomorphisms. However, if you take P to be of type 2, meaning that P is an almost complex structure J, then the Smith equation reduces to exactly the Cauchy-Riemann equations. And your Smith maps are J-holomorphic maps. We've seen what happens when you take P to be of type 3. If P is the vector cross product corresponding to a G2 structure, you get precisely the associative Smith maps. And finally, you can take the vector cross product to arise from a spin 7 structure on an 8-manifold. This gives you this PDE right here, and the solutions are called Cayley Smith maps. These are conformal parametrizations of Cayley 4-folds inside a spin 7 8-manifold. We won't really talk about this last case, but it is essentially completely analogous to type 3. So all of this apparatus, this entire definition was, of course, this was defined by Smith in his 2011 PhD thesis. Of course, he didn't refer to these maps as Smith maps. I think he called them multi-holomorphic or something. But after defining these maps, he showed that they satisfy some of the same geometric properties as J-holomorphic maps. So, for example, the Smith equation is conformally invariant. Right? If U is a Smith map, then so too is U circle F, where F is an orientation-preserving conformal diffeomorphism of the domain. Moreover, as we've seen already, Smith maps are weakly conformal. Okay, that can be shown, for example, from the p-form characterization. Moreover, Smith maps, when they are immersions, their images are then calibrated submanifolds where they're calibrated by alpha. Right? So precisely if U is Smith, then U of the regular set is a p-dimensional submanifold of M that is calibrated by alpha. Okay, now of course alpha need not be closed, but if it is closed, then in this case, this image is homologically volume minimizing, and in particular is a minimal submanifold. So this is sort of a beautiful thing, I think, that the images of Smith immersions are homologically volume minimizing. And moreover, the maps themselves are homologically p-energy minimizing. Okay, so this is exactly as in the J-holomorphic map case. Recall that the p-energy is of a map is the integral of norm du to the pth power times this factor. And Smith proved this very general pointwise inequality. If you have any C1 map from a p-manifold to an n-manifold, and sigma and n and m rather have the structure that we've described, then the integrand, the p-energy density, as it were, is at least u star alpha. And interestingly, equality holds precisely when U is a Smith map. Okay, we saw this in the J-holomorphic map case. So what's interesting is when you integrate both sides, and let's assume that alpha is closed, as happens when you have a symplectic manifold or a G2 manifold. In that case, the left-hand side, when you integrate it, becomes the p-energy. The right-hand side is an integral that is topological. Right? It depends on the cohomology class of alpha and the homology class of, I guess you call it the homology class of U, as it were. So the point is that for any C1 map, you have this topological lower bound on the p-energy, and equality is attained precisely by the Smith maps. Excuse me. So this is a very interesting geometric characterization of these minima, for homological minima for the p-energy. And so in particular, Smith maps minimize the p-energy in their homology class, and in particular they are themselves p-harmonic maps. Okay, so given these strong analogies, really generalizations of geometric facts from the J-holomorphic map world, one might ask, to what extent do the analytic features of J-holomorphic maps generalize to the Smith setting? We discussed in part 1 7 analytic properties of J-holomorphic maps that are very important to symplectic geometry. And you can ask which of these are true for, let's say, associative or Cayley-Smith maps. And we've shown that, in fact, all of them are true after some suitable modifications that I will describe. Now you might think, oh great, like, how hard could this be? Certainly that's what I was thinking in the beginning of this project. We'll just take the proofs in the J-holomorphic map case and just carry them over and everything will go fine. But it turns out that the situation is a little more complicated than that for a couple of reasons. First of all, when you have a J-holomorphic map, U, the critical set is discrete. That's very convenient because it means that you can think of J-holomorphic maps as branched minimal surfaces, and there's all this minimal surface theory that you can use, for example. But when you have a non-constant associative Smith map, it's not clear whether the critical set is discrete. It's reasonable to conjecture, I think, that the critical set maybe has codimension 2 inside the 3-dimensional domain, so maybe it's some sort of curve, but it's really not clear, and you do have to worry about this critical set. It really kind of causes problems. Okay, a related issue, arguably a more serious issue, is that Smith maps are p-harmonic maps, and the p-harmonic map equation is not quite elliptic. It is degenerate elliptic when p is greater than 2. So when p equals 2, of course, you're dealing with genuine harmonic maps, and all these wonderful things are true, elliptic theory comes in, etc. But what's known about p-harmonic maps, certainly a lot is known, but the results in many cases are not quite as strong, and in fact can't be as strong. There are certain counterexamples when it comes to regularity, for example. So how did we get around these challenges? It's a bit of a long story. I'll very briefly summarize, but one thing was we did draw on existing results on p-harmonic map theory. There's many folks who have contributed to this theory, and we did exploit that. Moreover, The associative Smith equation, it has a very particular sort of algebraic structure. It turns out to demonstrate what's sometimes called a compensation phenomena. This occurs for other geometric PDEs, such as I believe the CMC equation and certain types of harmonic maps into spheres, for example. And the idea is then to exploit this H1-BMO duality, that there are a bunch of papers which use this technique. And the upshot is that we're able to get this very powerful epsilon regularity result. Powerful in the sense that it yields 4 out of the 7 analytic properties pretty quickly. Okay, so I want to now turn to state these results, these properties 1 through 7, and show you what's the same and what's different from the holomorphic map case. Okay, and I'm going to state everything in the case of associative Smith maps, but everything works just as fine, just as well for the Cayley-Smith maps from a 4-manifold into an 8-manifold as well. Okay, so our target will be a 7-manifold with a G2 structure. We're not going to assume at the moment that the G2 structure is closed or co-closed or anything like that. This is pretty general. Okay, we'll use the standard notation for balls centered at the origin. And let's recall what the 3-energy functional is here. Okay, so just like in the J holomorphic map case, we're able to get a soup estimate that we show that the soup of du cubed is controlled by the 3-energy. We're able to get an interior regularity result that says that W13 Smith maps, associative Smith maps, are in fact C1 alpha. And in general, you don't expect really to do better than C1 alpha on the critical set, again, because of the degeneracy of the 3-harmonic map equation. But on the regular set, which is the complement of the critical locus, then in fact U is C infinity. We're also able to obtain a removable singularities result, which says that an associative Smith map with finite 3-energy extends over isolated singularities to an associative Smith map everywhere. There is also an energy gap result. So if you have a G2 manifold, or sorry, a 7-manifold with a G2 structure, there's some constant, epsilon 0, a threshold, such that every associative Smith map whose domain is the round 3-sphere, or the 3-sphere with its round conformal structure, really, into M, if its 3-energy is less than this threshold, then in fact such a map must be constant. We also get really the direct analog of the compactness mod bubbling theorem from before. If you have a sequence of C1 associative Smith maps with uniformly bounded 3-energy, then after passing to a subsequence, there is a limiting associative Smith map such that your sequence converges to it in C1 loc off of a finite set. This finite set consists of what are known as bubble points, and this convergence of radon measures explains what you can expect to happen, essentially, at the bubble points. And once again, if you have a stronger bound a priori, so if you have a 4-energy bound or just a p-energy bound where p is strictly bigger than 3, then bubbling doesn't happen. Okay, the bubbling set is empty. And so, just as before, you can, if you have a sequence of associative Smith maps with uniformly bounded 3-energy, you are able to get bubble trees in the limit, right? And like I said, this is a very general construction that occurs anytime you have a geometric problem with these features. When you have a conformally invariant functional and a conformally invariant PDE, when you have a removable singularities result, an energy gap, and a compactness mod bubbling theorem, as we do, sequences of your objects after passing to subsequences with uniformly bounded functional or energy will converge to bubble trees in the limit. So we get bubble trees whose bubbles are associative 3-spheres where the domain has the round conformal structure. And moreover, we're able to demonstrate that the bubble tree has some very nice properties, just like in the J holomorphic map case. Here we assume that phi is closed, though it's likely possible that we can remove this assumption. So if the G2 structure is closed, we're able to show that there's no energy loss in the bubble tree limit. That is to say that the remaining energy is completely captured by the 3-energy, I should say, is captured by the bubble maps. And moreover, the bubble tree has no necks in a sense that is made precise in the paper. Okay, so those were the results. And I should mention that, really this is not the end. This is very much the beginning of, I think, a lot of, maybe there should be a lot of interesting work that can still be done, and there's a lot to explore really about associative Smith maps. There's really very basic questions that we don't know the answers to. So we don't know, for example, anything about the deformation theory of associative Smith maps. The deformation theory of associative three-folds has been well studied by several folks, starting with McLean, but there have now been numerous studies depending on whether your associative threefold is closed or has boundary or is asymptotically conical, or maybe your seven manifold has torsion or something. So there's many studies on this depending on different contexts, but we don't know about the deformation theory of associative Smith maps and how does that relate to the sort of immersion case in a way. We don't know the structure of the critical set. We do know that an associative Smith map, this is true more generally, at every point x in the domain, the rank of du has to it either has full rank, so it's an immersion at that point, or its rank is of du is 0. And so we really want to know what can be said about the critical set, because many more techniques will be available if we knew that the critical set was, let's say, discrete or codimension 2 or something. The existence question is likely very difficult. It would be very good to know when do associative Smith maps exist. Now, it depends, of course, what you mean by that. One has to state that properly. Here's one thing you could mean. If you have any associative threefold in a 7-manifold with a G2 structure, then, if you have an associative threefold, then you can, endow the domain with a conformal structure just by pulling back the conformal structure, and that will make your inclusion map or your immersion into an associative Smith map. So in that case, in that sense, associative Smith maps are at least as abundant as associative threefolds, but this is probably not what most people mean by existence. What they really mean often is specify a 3-manifold with a conformal structure in advance. If you do this in advance, are there any non-constant associative Smith maps? It's not clear, and certainly it's tricky, and it's not clear how optimistic maybe that one should really be. Certainly, there are the conformal structures on 3 manifolds can be it can be very complicated, I guess. I will say that what I think is interesting is that the existence question lends itself to two related problems about associative threefolds, depending on whether you take sigma to be simple or flat, or m to be flat. So if you take m to be the flat at R7, for instance, there's a very interesting open problem about associative conformal immersion. So if you have a conformal 3-manifold, can it be conformally immersed into R7 as an associative? I don't know the answer to this. I think even the local problem is rather non-trivial. Just can you locally conformally immerse as an associative any conformal 3-manifold? I don't think that's really known or at all obvious. On the other hand, you could take sigma 3 to be conformally flat and ask the following question: if you have a 7-manifold with a G2 structure, let's even say you have a G2 manifold, so phi is closed and co-closed, that's like the best case scenario, are there in general any conformally flat associative threefolds in M7? I think this is a very basic question. It's a very interesting question to ask. Certainly, again, locally, we do have associative threefolds, but conformally flat, I don't know, frankly. And I think these are important questions to further our understanding of associative Smith maps and just associatives in general. So there's a lot of work to be done, and well, thank you all for your attention.